Hello everyone, my name is Iman Mirzadeh and today I'm going to present our paper Dropout as an Implicit Gating Mechanism for Continual Learning. This is a joint work with Mehdad Farash Tabar and Hassan Qasemzadeh. Our agenda for today is first to review the catastrophic forgetting problem, followed by a definition of our research question. In the second section, we discuss how training a model with dropout will implicitly create a gating mechanism, where in section 3, we show this empirically in addition to other results. It's known that neural networks suffer from the catastrophic forgetting problem when they face a sequence of tasks rather than a single task. Basically, they forget the previous task as they learn newer ones. We can see in the figure that as the network learns task 2, its performance on task 1 drops, and as it learns task 3, its performance on task 1 and 2 drops, and so on. One interesting observation is that networks that are trained with dropout forget at a slower rate. We have shown this in our paper, but you can also find this phenomenon in other papers across the literature. However, an important question, which is why this is happening, is not studied well. We try to answer this question in our work. We argue that training with dropout and learning rate decay implicitly creates a gating behavior in the network such that for different tasks, different paths of the network are active. To see the reason, we need to study the dropout dynamics first. In the figure below, we can see that dropout regularization pushes neurons to be either always active or always inactive. Intuitively, in a network with gating mechanism, for each task, only a specific set of neurons at each layer are active. Having some active and inactive neurons for a task is equivalent to mimicking this mechanism, and dropout does that. Finally, learning rate decay helps preserving the gates throughout the continual learning experience since it controls the amount of gradient update we apply. To see the gating mechanism in action, we plotted the activation pattern of neurons for the first layer of two networks that are tasked to learn 5 tasks. The upper figure shows a network trained without dropout, while the lower figure shows a network trained with dropout. On the x-axis, we have neuron indices, and on the y-axis, we have task numbers from 1 to 5. The goal here is to see which neurons are active for each task. We can see that in the upper network, which is trained without dropout, almost all neurons are active for each task, where in the network below, which trained with dropout, for each task, only a specific set of neurons are active. In addition, we show that for a specific task, which here is the first task, the gating mechanism is consistent throughout the continual learning experience, meaning that the neurons that become active for task 1 after finishing task 1 will also be active for this task after finishing task 5. Here, the goal is to show that for a specific task, the active and inactive neurons remain roughly the same throughout the learning experience. In our second result, we discussed the plasticity stability dilemma. Ideally, a neural network requires plasticity for the acquisition of new knowledge in addition to stability, which prevents forgetting of the previous knowledge. However, naively trained neural networks, like the one on the left, are very plastic and not stable, which leads to poor performance in continual learning problems. We show that by increasing the dropout rate and learning rate decay from left to right, the stability of network will increase and the plasticity will decrease, meaning that a plastic network will learn new tasks with higher accuracy, but it also forgets the previous task faster compared to a stable network. Finally, we show our preliminary result for comparing the performance of a stable network with other state-of-the-art methods on 3 benchmarks, each with 20 tasks. As illustrated, the stable network performs consistently better than the other algorithms, while it doesn't use an episodic memory. In conclusion, we discussed an interesting question about the effectiveness of dropout in continual learning and argued that this is due to the gating mechanism. We later illustrated this claim in our experiments. Finally, we showed the effectiveness of increasing the network stability for the case with large number of tasks on 3 benchmarks. Thank you for your patience and feel free to contact me if you have any further questions. I'll be glad to help.